behavior stems from the fundamental transformer equations, specifically the relationships between voltage, current, impedance, and the turns ratio. We can describe the primary voltage, denoted as volt sub P, as equal to the secondary voltage, denoted as volt sub S, multiplied by the ratio of the number of primary turns, denoted as N sub P, to the number of secondary turns, denoted as N sub S. Similarly, the primary current, denoted as amp sub P, can be expressed as the secondary current, denoted as amp sub S, multiplied by the inverse of the turns ratio, that is, N sub S divided by N sub P. A key relationship connects the primary impedance, denoted as C sub P, to the secondary impedance, denoted as C sub S. It states that Z sub P equals Z sub S multiplied by the square of the turns ratio, that is, N sub P slash N sub S squared. Now, considering this last equation, Z sub P equals Z sub S multiplied by N sub P slash N sub S squared, it becomes clear that changing the secondary impedance, C sub S, directly impacts the primary impedance, C sub P. The relationship is not linear, but rather proportional to the square of the turns ratio. This occurs because a transformer operates on the principle of magnetic coupling. The primary winding, when energized by an alternating current, generates a magnetic field. This magnetic field, in turn, induces a voltage in the secondary winding. The magnitude of this induced voltage is directly proportional to the turns ratio N sub P slash N sub S. Consequently, the current flowing in the secondary winding is inversely proportional to the same turns ratio. Combining these voltage and current relationships, we find that the impedance observed on the primary side is proportional to the square of the turns ratio. In essence, the transformer transforms not only voltage and current but also impedance, scaling it by the square of the turns ratio. This impedance transformation is a crucial aspect of how transformers function in various electrical circuits. For example, consider a scenario where we want to match the impedance of a source to the impedance of a load for maximum power transfer. Transformers are frequently used for this purpose. By selecting the appropriate turns ratio, we can effectively transform the load impedance to match the source impedance. Firstly, let's delve deeper into the concept of impedance. Impedance, represented by Z, is a measure of the opposition to the flow of alternating current in an electrical circuit. It is analogous to resistance in a direct current circuit but includes the effects of capacitance and inductance in addition to resistance. Impedance is a complex quantity having both magnitude and phase. A magnitude of impedance, typically measured in ohms, represents the overall opposition to current flow. The phase angle represents the phase difference between the voltage and current waveforms. In a purely resistive circuit, the impedance is simply equal to the resistance, and the phase angle is 0 degrees. In a circuit containing both resistance and reactance due to inductance or capacitance, the impedance is a complex number and the phase angle is non-zero. The impedance transformation property of transformers is essential for efficient power transfer. Maximum power transfer occurs when the source impedance is equal to the complex conjugate of the load impedance. In many practical situations, the source and load impedances are not matched. A transformer can be used to match these impedances, ensuring maximum power transfer. Secondly, let's consider a practical example. Suppose we have a power amplifier with an output impedance of 8 ohms and we want to connect it to a speaker with an impedance of 4 ohms. Connecting the amplifier directly to the speaker would result in a significant impedance mismatch, leading to reduced power transfer and potential distortion. To solve this problem, we can use a transformer with a turns ratio of 2:1. The transformer will transform the 4 ohm speaker impedance to an 8 ohm impedance as seen by the amplifier, resulting in a matched impedance condition and maximum power transfer. Thirdly, consider how impedance transformation is also crucial in power distribution systems. Power is typically generated at high voltages and low currents to minimize transmission losses. However, most electrical devices operate at lower voltages and higher currents. Transformers are used to step down the voltage and step up the current at various points in the power distribution system. These transformers also transform the impedance levels to ensure efficient power delivery to the end users. The turns ratio of the transformer determines the voltage and current transformation ratios, and consequently the impedance transformation ratio. Fourthly, the design and selection of transformers for specific applications require careful consideration of the impedance characteristics of both the source and the load. Understanding the impedance transformation property is essential for optimizing the performance of electrical circuits and systems. The impedance in looking into the primary is the applied volts divided by the resulting primary amps. Since the transformer is an impedance converter, that means that the secondary impedance is reflected back to the primary side, scaled by the square of the turns ratio. Therefore, a step-up transformer, that is, one where N sub P is less than N sub S, has a higher impedance on the secondary side than on the primary side. Conversely, a step-down transformer, where N sub P is greater than N sub S, has a lower impedance on the secondary side than on the primary side. Fifthly, the impedance transformation also plays a role in isolation. Because the primary and secondary windings are electrically isolated, the transformer can provide a degree of isolation between the source and the load. This isolation can be important for safety reasons such as preventing ground loops or protecting sensitive equipment from voltage surges. The impedance transformation property also contributes to the isolation characteristics of the transformer. The impedance transformation, as discussed, hinges on the turns ratio. Let's explore that relationship in more detail. The turns ratio, denoted as N sub P / N sub S, is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding. This ratio is a fundamental parameter of the transformer and determines its voltage, current, and impedance transformation characteristics. Firstly, the voltage transformation ratio is directly proportional to the turns ratio. If the turns ratio is 2:1, the secondary voltage will be twice the primary voltage. Conversely, if the turns ratio is 1:2, the secondary voltage will be half the primary voltage. Secondly, the current transformation ratio is inversely proportional to the turns ratio. If the turns ratio is 2:1, the secondary current will be half the primary current. Conversely, if the turns ratio is 1:2, the secondary current will be twice the primary current. Thirdly, the impedance transformation ratio is proportional to the square of the turns ratio. If the turns ratio is 2:1, the secondary impedance will be 4 times the primary impedance. Conversely, if the turns ratio is 1:2, the secondary impedance will be 1/4 of the primary impedance. The turns ratio is a key design parameter that determines the overall performance of the transformer. It must be carefully selected to meet the specific voltage, current, and impedance requirements of the application. Let's also discuss the limitations and considerations when applying the impedance transformation principles. Firstly, transformers are not ideal devices and have losses associated with them. These losses include core losses, winding losses, and stray losses. These losses can affect the overall efficiency of the transformer and can also impact the impedance transformation characteristics. Secondly, the impedance transformation is frequency dependent. The impedance of inductors and capacitors varies with frequency, which can affect the impedance transformation ratio of the transformer. Thirdly, the impedance transformation is also affected by the loading conditions. The impedance seen by the primary winding will vary depending on the impedance of the load connected to the secondary winding. Therefore, it is important to consider the loading conditions when selecting and applying transformers. Fourthly, the impedance transformation is also affected by the nonlinearities in the core material. The core material can saturate under high flux densities, which can lead to distortions in the voltage and current waveforms and can also affect the impedance transformation characteristics. Fifthly, the impedance transformation is also affected by the temperature. The resistance of the windings varies with temperature, which can affect the impedance transformation ratio of the transformer. It is important to consider the temperature variations when selecting and applying transformers. In summary, the impedance transformation property of transformers is a fundamental concept that is essential for understanding how transformers function in electrical circuits and systems. It is important to consider the turns ratio, the frequency, the loading conditions, the core material, and the temperature when selecting and applying transformers. The relationship between primary and secondary impedance is crucial for understanding transformer operation and applications. Remember, Z sub P equals Z sub S multiplied by N sub P slash N sub S squared. The understanding of this equation is critical for electrical engineers and technicians working with power systems, electronics, and related fields. Consider the scenario of designing a power supply. The power supply needs to efficiently convert alternating current volts from the mains to direct current volts suitable for electronic devices. A transformer is a key component in this process. By carefully selecting the turns ratio of the transformer, we can achieve the desired voltage transformation and impedance matching, optimizing the power supply's efficiency and performance. Or consider audio amplifiers. Audio amplifiers use transformers to match the impedance of the amplifier's output stage to the impedance of the speakers. This impedance matching ensures maximum power transfer and minimizes signal distortion. The turns ratio of the transformer is chosen to match the impedance of the amplifier to the impedance of the speakers, typically 4 ohms or 8 ohms. Transformers are also employed in various measurement instruments. For example, current transformers are used to measure high alternating current currents. The current transformer steps down the high current to a lower, more manageable level, which can be safely measured by an ammeter. The turns ratio of the current transformer is carefully chosen to provide an accurate measurement of the high current. Now let's consider some additional factors that can influence the impedance transformation. Firstly, leakage inductance. Leakage inductance is the inductance associated with the magnetic flux that does not link both the primary and secondary windings. Leakage inductance can cause voltage drops and can affect the impedance transformation characteristics of the transformer. Secondly, winding capacitance. Winding capacitance is the capacitance between the turns of the windings. Winding capacitance can cause resonant effects and can affect the impedance transformation characteristics of the transformer at high frequencies. Thirdly, core losses. Core losses are the losses associated with the magnetization and demagnetization of the core material. Core losses can cause heating and can affect the efficiency of the transformer. The core losses are dependent on the frequency and the flux density in the core. Fourthly, copper losses. Copper losses are the losses associated with the resistance of the windings. Copper losses can cause heating and can affect the efficiency of the transformer. The copper losses are dependent on the current flowing through the windings. These factors can influence the impedance transformation characteristics and must be considered when designing and selecting transformers. Also, transformers are used in high-voltage power transmission systems to step up the voltage for efficient transmission over long distances and then step down the voltage for distribution to homes and businesses. The impedance transformation provided by the transformers is crucial for maintaining voltage stability and minimizing transmission losses. Furthermore, the selection of the transformer core material plays a significant role in determining the transformer's performance and impedance characteristics. Common core materials include silicon steel, ferrite, and amorphous alloys. Each material has its own advantages and disadvantages in terms of permeability, core losses, and saturation flux density. The choice of core material depends on the specific application requirements. Transformers also find application in renewable energy systems such as solar and wind power. They are used to connect the renewable energy sources to the grid and to match the impedance of the renewable energy sources to the grid impedance. In addition, transformers are used in electric vehicles for charging and for powering the electric motor. The transformers in electric vehicles must be compact, lightweight, and efficient. Let's also explore the concept of reflected impedance in more detail. The impedance seen looking into the primary winding of a transformer is not simply the impedance of the primary winding itself. Instead, it is the reflected impedance of the secondary winding, scaled by the square of the turns ratio. This reflected impedance is what determines the current flow in the primary winding. This reflected impedance is a crucial concept in understanding how transformers work and how they interact with other circuits. To summarize, the impedance transformation property of transformers is a fundamental principle that is essential for understanding how transformers function in electrical circuits and systems. This property is governed by the turns ratio and is affected by various factors, including leakage inductance, winding capacitance, core losses, copper losses, and the core material. The impedance transformation property is widely used in power systems, electronics, audio amplifiers, measurement instruments, renewable energy systems, and electric vehicles. By understanding the impedance transformation property, engineers can design and select transformers that meet the specific requirements of their applications.